in the back propagation like this, we see that because the derivative of the sigmoid function it takes the value very less than 0.25, which in turn becomes very, very less with the increasing number of layers, and that is how the gradients vanish, and earlier layers they get almost no gradient. So that is how the weights don't update and the network stops learning from the earlier layers. So this is the vanishing gradient problem. And the opposite of this, when the derivative becomes, not in the sigmoid case but in other cases, when the derivative becomes greater than 1 or large weights are used, in that case the gradients they blow up layer by layer. That is the exploding gradient problem. Okay. So in these cases what happens is we use special initialization techniques like the Xavier or the He, and activations like the ReLU. They are used to take care of these issues of vanishing and exploding gradient. So you can see that in this example, we had only considered a very oversimplified example with only one node in each layer. So when you take this same thing for multiple layers, the multiplication also becomes in the form of matrix multiplication, and then you have the square Jacobians and so on. So the effect of activation functions like the sigmoid, it tends to encourage the vanishing gradient problem in actual real scenarios. Uh, the second is now the tan hyperbolic. So this is also commonly used in deep learning when a zero centered output is desired, and it gives slightly better gradients than sigmoid, but it also suffers from the vanishing gradient problem. The formula for this is e power x minus e power minus x upon e power x plus e power minus x. This outputs between minus 1 and 1, unlike the sigmoid, which gave us the output between 0 and 1. The shape of this is again S shaped, centered around 0, and negative inputs give negative outputs, which helps the in the optimization. So the main advantages of tan hyperbolic activation function is that it is giving us the zero centered output. So that is why it is used mostly in the recurrent neural networks, where it helps the gradients alternate around zero, helping in the better training. It The second advantage is that it has stronger gradients. Why? Because it keeps the gradient flow stronger than that compared to sigmoid. It also gives us smooth output, so that this is good for capturing fine grained patterns, like that is required in the text classification problem or sentiment analysis problem. So tan hyperbolic activation function is basically popular in the natural language processing neural networks, like the text classification or the sentiment analysis, etc. The disadvantage is again that of vanishing gradients, and computationally it is expensive because it uses exponential, which slowers, which is slow to compute. Okay, so to overcome this, there is another activation function which is widely used in deep learning today in the hidden layers, is the rectified linear unit, that is the ReLU. So which is given by f of x is equal to maximum of 0 comma x. So this gives us the output zero. So it was deactivated using this ReLU function example that I gave in the beginning of this session. The main advantages here is it is computationally efficient because there are no exponentials involved in the function. Function is very simple. It is just maximum of 0 comma x. It also takes care of the vanishing gradient problem, because there are because of the strong gradient for x greater than 0. Okay, there is no gradient saturation. uh, it's easy training even with many layers. Okay, disadvantages that it is not differentiable at 0. So theoretically it is non smooth. You can see a sharp corner, but this is not such a big issue in practice. In practice, the big issue is of dying neurons. Neurons get stuck at 0. So uh, and as a result some neurons become inactive. So if a neuron gets stuck in negative zone, it never activates again. We will see it mathematically in a while. And then it is also not zero centered. So all the outputs are greater than equal to 0. So which results in slower convergence due to the shift. So basically ReLU is used in almost all the hidden layers. So let us see the problem that it is having, the dying neuron problem. Uh, Neuron problem with ReLU. ReLU of x is to x if x then equal to 0 and 0 if so what happens is that if case in the case when you have negative pre-activation values, in that case what happens, so if you have the pre-activation values are given by the weighted sum, that is W transpose X plus B. So why this transpose? Because we are considering it to be a matrix in the multi-layer, multi-neuron problem. So if your Z is less than equal to 0, then what happens? ReLU of Z. So when you apply the nonlinearity with the ReLU activation function, you get it as 0. And its derivative also becomes 0. Okay. So this means the output is 0 and the gradient will also be 0 during the back propagation. So hence your weights will not be updated because of the chain rule. So del z upon del w will implies 0 dot x, which is 0. So there is no update to the weights. Okay. So if this keeps happening, the neuron is dead because always the output is 0 and it never updates. Case 2 is when you have high learning rate. High learning rate. So in this case, if the learning rate is too large, that is eta is too large. So then in that case, what can happen? The weights can jump in a way uh, in a way that this Z, the pre-activation, becomes negative. for all inputs. So again, we fall into the same problem. So ReLU never activates because it will again go back to this scenario. Okay. So mathematically, this is the condition of a neuron being dead because the ReLU never activates and because of its derivative also going to zero. So such neurons are never updated and they do not contribute anything to the learning. So to mitigate this problem, there was this leaky ReLU activation function proposed. This is very similar to the ReLU, but a bit different that it allows for a leak, as the name says, leaky ReLU. So this is given by the leaky ReLU is given by X, same as before for positive values is not equal to 0. So hence the weights can still be updated and the neuron may come back to life. So this is about the leaky ReLU function, which fixes the dying ReLU problem where the neurons were getting stuck outputting 0. Here, unlike the ReLU, the range has become from minus infinity to infinity, and you can see that the graph, a tiny slope, there is a tiny slope for the negative values, preventing a flat region like this. Okay. So this allows negative outputs unlike the ReLU. So biggest advantage is that it solves the dying ReLU problem. It doesn't get stuck in the vanishing gradient problem. Small gradients for negative values. So the learning continues and the slope, the alpha in the leaky ReLU is also learned. Okay. So these are the advantages. The disadvantages include that uh, fixed there is a fixed bias for the negative inputs, so it might not generalize well in all the tasks. Okay. And the second disadvantage is that it's not always performing better than the ReLU. Some data sets or the networks, they work fine with this leaky ReLU. Some may work fine with the plain ReLU as well. So this is about the leaky ReLU function. So this is also quite popularly used in the deep CNNs for small data sets. Uh, uh, Text classification with sparse features when we want all the use this because they want to avoid the dead neurons. So when okay, so making this negative side curves gently. Okay, unlike the ReLU and the leaky ReLU. In the leaky ReLU there was this sharpness, and in the ReLU there was again this sharpness without the slope. Okay, so this also is used in many simple examples in the deep learning, like the image classification with noisy data, because smooth output is required, which will help stabilize the gradients across all the convolutions, okay, for the image classification. uh, where we want the negative activations help center the network output for the faster convergence. There also ELUs used. So such kind of scenarios arise in the speech recognition, where we want to reduce the sharp zero cutoffs for better learning in small gradient areas. There also ELU is used. These kind of scenarios arise in the biomedical data, where it is imbalanced as well as sparse. So the advantages is that it comes with a smooth transition at x is equal to 0, as seen here from the graph. There is negative outputs which approaches minus alpha. So it makes the mean activation closer to 0, which help convergence, and also it reduces the vanishing gradient problem. Okay, the disadvantage is that it is slower to compute than ReLU, because it uses exponential for negative x values. It may explode if not normalized, because large x value means large output. So these are some kind of problems. So we can use ELU for small data sets when better generalization is required as compared to ReLU. You can use it for noisy networks, deep and noisy networks where smooth curves are required. And you can also use it when you are experiencing dead neurons. So this in these cases also ELU is used. Next is the softmax activation function, which is mainly used in the output layer of the deep neural networks for multi-class classification. So what it does is it converts the scores or the logits from final layer of a neural network into probabilities. Each output value represents the probability of a class, and all class probabilities sum to 1. So here is the mathematical representation of the softmax, that is e power zi by summation e power zj. So zi is the score for class I, and the denominator is the sum over all the classes. So output range is again 0 and 0 to 1, and it can be interpreted like the probabilities. So this is also, as I said, that this is used at the output layer. It converts the scores into probability. Uh, uh, because the large digits, they can lead to near zero probability for others. Our strategies expensive, involves exponentials and summation. That is why, and it is poor for closed class scores, because it is hard to interpret when the probabilities are similar. Basically, the softmax function is like a voting system. If each output neuron votes for a class, the strength of the vote is converted into a percentage of confidence. So the one with the highest confidence gets selected, like the winning candidate in the election. Then we have this swish activation function, which was recently developed by the Google researchers, and it is designed to combine the best features of sigmoid and ReLU while avoiding the main issues that were present in the sigmoid and the ReLU, that is the vanishing gradient and the dying neuron. So here the formula is x times sigma of x, where sigma of x is the sigmoid. So it multiplies basically the input with its sigmoid, which creates a smooth non-monotonic curve. So this is inspired by gating mechanisms, which is used in LSTM and highway networks, but simplifies it by reusing the input. Its output range is unbounded on the positive side, and negative side smoothly decreases. It is uh, the advantages of this are that there is no dying ReLU problem, because a swish is smooth and non-zero for negative inputs. Higher accuracy. uh, when it was proposed, it was proven to outperform the ReLU in image models like the efficient net. It's adaptive because it works well across a range of batches and the data types. Disadvantage is that it is more expensive because it needs both the input and the sigmoid, so this is kind of a more computation. And it is new and less tested, so it may require more generalize I mean it may require more experiments to generalize it across many other tasks. So for positive inputs, Swish behaves like a ReLU. For negative inputs, it reduces the value instead of dropping it like ReLU. So this allows for some gradient flow at least. So this was about the Swish activation. Then there is also something called as max out activation, which is advanced alternative to ReLU and ReLU. To the shape of the activation. At the same time, it is preventing dead neuron problem and neurons die. Yes, not audible. Now also it is breaking. Fine now. I think today there is some issue going on. Is it fine now? Can I proceed? Or now?
Yes, ma'am, it's fine now.
Okay. So it is the max out is also preventing dead neurons, because it is avoiding the fact that in ReLU neurons could die if they always output zero. So max out avoids this because at least one linear function out of these will be getting selected, and they keep outputting a non-zero value. And it works well with dropout also. Drop randomly turns of neurons during the training. Max out
Again, noted. Hello. Ma'am, you are not audible again.
Uh, am I audible? Hello? Hello? Am I audible?
Yes, ma'am, but voice is breaking, then you are not audible.
It's breaking a lot.
Yes, ma'am.
Okay, so what I will do is I'll rejoin once again, try to see if it is not breaking. I'll rejoin in a minute. Hello, am I audible now?
Yes, ma'am.
Can you see the screen? Is my screen visible?
Yes, ma'am.
Yes, ma'am, it's visible.
And my voice is also clear?
Yes.
Okay, so we were talking about max out, which takes two linear combinations at a time. So you need two sets of weights and biases instead of one, which doubles the trainable parameters. So this is one of the disadvantage of max out. The another one is higher computational cost, because more computations per neuron are to be done because of calculating multiple linear out, uh, outputs. Should not use max out. Perhaps you can go for some other simpler activation functions, like the relu, or even sigmoid for that matter. This is the scenario. My voice is fine, I think. Is it okay? Audible?
And it's breaking
Yes,
sometimes.
ma'am.
It's still breaking. Okay, so I think, is it okay or still breaking?
Okay, ma'am, you can start.
So soft plus, next is the soft plus activation function. So this is a smooth alternative to the loop.
Not audible, ma'am.
The output is zero and the gradient is also zero. So that was the red neuron problem that we saw.
Ma'am, you are not audible from past 2 minutes. Please repeat.
Am I audible now?
Yes, ma'am, but after every 2 minutes, the voice should go on.
One second. I'll just change my network. Am I audible now?
Yes, ma'am.
Is it still breaking or I mean, my voice is still breaking?
Yes, ma'am, slightly.
Am I audible?
Yes,
Is
ma'am.
my voice still breaking?
No, ma'am.
My screen is visible?
Yes, ma'am.
I'm visible.
Okay. Okay, so uh, we were in the this soft plus activation function, which is basically a smooth alternative to ReLU. As you can see the graph also, the ReLU also had the similar kind of graph, but with a sharp corner here at 0. This is not having that. So this is also mitigating the vanishing gradient and dead neuron problem. So if you use ReLU for the input x is equal to -2, the output was 0 and the gradient was also 0. So that was the dead neuron problem. But with the soft max, if you input -2 here, you will get 0.13 something. And when you take the derivative of this, it will also give you a non-zero value. So it is contributing to the learning during the back propagation. I hope my voice is clear.
Yes, ma'am, it's fine.
So because it's differentiable everywhere, the optimization algorithms like the ADAM or SGD uh, can move smoothly in the parameter space, improving the convergence in some cases. So this is giving us the better optimization landscape. The disadvantages here is that it is having slower computation because of the involvement of exponential and log in the definition. Both are expensive operations as compared to the ReLU's simple comparison. So training can be slower, especially if you are using a large scale network. It's not zero centered, so it can cause a biased gradients problem, which again may result in slow convergence. uh, Saturation for large values, so for very large inputs, uh, mm, the gradient approach, the approach is one, and learning still slows slightly due to the logarithmic nature. So the when to use this soft plus is when we want to avoid the dead neuron problem and we need smooth derivatives. For example, the probabilistic models. But it is not suitable for large networks which need fast training. Here already we have this log and exponential, so which is quite computationally expensive. So this kind of activation function may not work for large networks which require fast training. Okay. uh, then we can avoid it for running on low power devices also. So and also we can consider alternatives when we require zero centered outputs. So theoretically or from research scenarios, this is a more suitable activation function. Okay. And uh, and for the sparse model requirements also. So soft plus is a nice, smooth and safe alternative to the ReLU, especially when you want stable gradients and you're building a probabilistic model, or you want to avoid the dead neurons. However, it's computationally costly and non-zero centering, so that is why it makes it a less popular choice for high speed or the resource constraint applications. Now here we compare the gradient dynamics of activation functions. Why gradient dynamics matters? As we know that when we are training a deep neural network using the gradient based optimizers, we rely on the back propagated gradients to update the weights. So if these gradients vanish or they explode, the learning is hampered. So activation function It's a job of activation function to allow for stable and non-zero gradients over a useful input range. So sigmoid, as we have already seen, that it is smooth and bounded, but for very large or small inputs, the derivatives, they approach zero. So as you can see here, for very large or the very small inputs, that is mod x greater than 4, the derivative is approaching 0. Okay, these lines. It is not zero centered also. Okay, so this can cause biases in the gradient update direction. This is bad for deep layers because the early layers, they learn very slowly due to very tiny gradients. Then we have the tan hyperbolic, which has its advantages in zero centered outputs between -1 and 1. It is giving us the steeper slope in the center as compared to the sigmoid. So but it still saturates at the extremes, which causes the vanishing gradient problem, okay, though it is less than the sigmoid. Then we saw the ReLU. So this is kind of a linear for x greater than 0, where the gradient is also 1. So it is mitigating the vanishing gradient problem, and it promotes the efficient learning. But for the negative, for the negative inputs, it is giving us the zero gradient, which causes the dead neurons that never activate again. So that is another disadvantage, and it is also not zero centered. So to mitigate this, we saw the leaky ReLU, which allowed for a small negative the leaky ReLU graph had a bit of slope here, which allowed for small negative slope. Okay, so there is a small negative slope. This is just a technical error here. As we saw earlier slide with the leaky ReLU, there was this there was, yeah, this slight negative slope here, which is not visible in that slide. Anyhow, I hope my voice is clear.
Yes, ma'am.
Okay. So this reduces the dead neuron problem because it is giving some alpha value for the negative inputs. It is again not zero centered. So gradient updates can be biased in one direction. Then we saw the ELU. ELU was more smooth and differentiable because of the involvement of exponential. It is giving us the zero centered output, uh, allowing the gradient updates to be balanced, and it helps the deep neural network converge faster and more reliable in practice. So it combines basically the benefits of ReLU and tan hyperbolic by avoiding the dead neuron as well as the zero centered. So that is why it is used in deep architectures. Then we saw the softmax. So this outputs probabilities used in multi-class classification, but it is not used in the hidden layers, only used in the output layer of the classification networks. Okay, it converts the raw logits into interpretable class probabilities. So this softmax works best for the cross entropy loss. So now we have the three modern activation functions: the swish, max out, and softmax. Here we have plotted the gradient dynamics of them. So the swish, unlike the ReLU, it bends down for negative inputs, helping the gradients flow. It retains the gradients for the negative inputs, which reduces the dead neuron problem. And of course, it avoids the vanishing gradient problems also. Max out, on the other hand, is learning the piecewise linear regions, generalizing the ReLU activation function. but because of increased parameter, each unit has multiple sets of weights, so it becomes computationally more expensive, and the gradient looks like a step function. So, and the soft plus, finally we have the soft plus, which again is a smooth version of ReLU, as can be seen here, and never zero gradient. Okay, so this is again, you can see from its gradient mm, gradient curve also. It is not zero centered like the sigmoid, and this can bias update and become slower in convergence. So Swish, Max Out, and Soft Plus are the modern activation functions. Swish is excellent modern choice for deep models because it retains gradients and helps avoid saturation, as can be seen from this graph. Max Out is very flexible but impractical due to computational cost, and Soft Plus is a nice theoretical choice but less practical benefit over ReLU in many of the problems. So these are the key properties that we just discussed, and the best suited scenario where these activation functions are used, like the sigmoid is generally used for binary classification in the output layer. Tan hyperbolic is used in the hidden layers for the NLP problems. ReLU is used for convolutional neural networks in the hidden layers. Leaky ReLU is used more in deeper networks for the general purpose usage. ELU is also used in deep architecture. So you have to basically empirically find out with the given problem at hand which of these is working well for your network in the hidden layers. Whether you require more stability or more smooth gradients, or and so on, depending on the problem at hand, uh, you can gauge which activation function is working better and giving you best results. So Swish is found to be very efficiently giving high accuracy in the networks like the efficient net. Soft plus is used in the probabilistic models when smoothness is needed. Max out is again when you require the robustness in your model, and not the time constraint or not the computational constraint. And soft max is for the multi-class classification for the output layer. So the general tip here of choosing the right activation function is that you start with ReLU in the hidden layers, because ReLU is simple, efficient, and it works well in most cases. Only switch if performance is poor. Example, unstable gradients or poor accuracy. Avoid in the hidden layers the sigmoid and the tan hyperbolic activation functions, because these functions saturate for large positive or the negative values, as we have seen in the previous slides. So this causes vanishing gradients, making the learning very slow or ineffective in the deep networks. I hope my voice is clear.
Yes, ma'am.
Then we have the Swish. It is suitable for deep networks which are having more than 40 layers. So this is recommended for very, very deep architectures like those found in the image classification or the transformer. Okay. Uh, so, and so the key observations here are that ReLU is the default go-to for hidden layers. Use your task specific functions at the output, and avoid the activation functions which make your gradients vanish, okay, in the hidden layer. And you can also choose Swish or advanced activation functions like we saw in the end for very, very deep and sensitive models. So finally, to summarize, why are activation functions crucial? Because it regulates the gradient flow. Back propagation uses gradients to update weights. So if gradients are too small or too big, training breaks. To shape the loss landscape, the shape of the loss surface clearly affects how easily and smoothly the optimizer can find the minimum. So activation function clearly shape the loss landscape. These control the learning dynamics very well. The activation functions, they impact how fast or how well the model learns, as we saw in previous slides. Then, of course, they introduce the non-linearity. Without non-linearity, the model is as good as a linear function, no matter how many layers we are putting into. Then we have the task-specific adaptation. Different tasks need different output behaviors, so you can choose accordingly from the activation functions. So these are like activation functions are like the gears in a machine. They will control how fast and smooth the training goes. They will shape the road, that is the loss landscape, to the destination, and they allow your model to think non-linearly in the real scenario. Okay, so this is a small empirical impact of different activation function on MNST dataset. I will tell more about this dataset in the lab session. So for now, you can see that here we have plotted the training loss on the on the y-axis, and the epoch, that is the training progress, on the x-axis. So you can see that the sigmoid has the slowest and the highest loss, okay, of all the other activation function. So this confirms the fact that it suffers from the vanishing gradients. So basically, in the MNST data set, which is basically handwritten digit classification data set. So there are 10 classes here, and there are around 60,000 images, 70,000 images total. So in this data set, clearly you can see that the sigmoid is suffering from the vanishing gradient problem, even at a 3-layer feed-forward network. Okay, soft plus is smoother. This brown line is smoother but converges slowly as compared to the others. Relu, leaky Relu, Swish, and ELU. So you can see here, Relu, they are all coinciding here. Relu, leaky Relu, Swish, and ELU, they are achieving faster and lower loss as compared to the sigmoid and the soft plus. So you can see it here clearly. So you can see the tinge of green here, which is the Relu. This graph shows the test accuracy. Y-axis, again, we have the test accuracy, and the x-axis is the epoch progress. Okay. Here you see that leaky Relu and Relu, that is the green and the red line, and Swish also, so that is the pink line here, reach the highest accuracy. Okay, the leaky Relu, that is the red line, Relu, that is this line, green one, and Swish, that is the pink line. They reach the highest accuracy. Sigmoid again performs the worst here, that is the blue line here is performing the worst, and ELU and soft plus, that is this purple and brown, this one, perform moderate only, but not the best. So this is showing the impact of different activation functions on the training and the testing. So based on this, what we can conclude that in this experiment, which was trained on only 3-layer feed-forward neural network on MNIST data set, which is a handwritten digit data set having 10 classes with 70,000 images. So how do we analyze which performed best? So the criteria is that it should be fast, and if we set the criteria to be having fast and low training loss. Fast convergence and training loss is also less, and uh, high and consistent test accuracy. So based on these criterias, in the training loss, leaky relu, swish, they have shown the faster convergence, faster drop of the loss, and lowest final loss. In the test accuracy, the uh, leaky relu is quite consistent, and it is achieving the highest test accuracy by the final epoch. Okay. Relu and swish are closely following this leaky relu. So this starts well, then the leaky relu, and goes till, I mean, the testing is not that consistent, but yeah, that is, they achieve to the close, that is the 98% accuracy kind of, or means. So leaky relu is the best performing activation function in this experiment, both in terms of training as well as testing. So this is just a demonstration for learning purpose. This way you can also find out which activation function is working best for your research problem or for your model, and gauge how the optimization is happening. So with this, I finish the session on activation functions. Hope my voice is clear now.
Yes, ma'am.
Okay. So are there any questions here? Any questions here?